let's go into some of the basics of just linear regression stuff at the start here, and talking about loss before we get into some of the nitty-gritty linear algebra that is involved with linear regression when you're going to do it via gradient descent, or ordinary least squares for that matter. So let's start out with some linear regression basics. Linear regression basics. It is not the best handwriting. So for example, wherever we use linear regression, say we have some data on housing prices and square footage. Say we have some data on housing prices and the square footage. Okay, let me just change this real quick. So we can draw a little axis here. Bloop, sure. Looks good. So maybe it's kind of something like that. I don't know, right? So you've got I'm putting up a price on the vertical and square footage on the horizontal. So a single line then can approximate this relationship pretty nicely. So kind of what we might expect, as square footage goes up, the price goes up as well. So I can try my best to fit a line through this. Maybe something like that. Maybe move it up just a little. I don't know. That's not bad. I'll leave it like that, right? So a single line's a pretty good approximation here, right? So we can use a single line can approximate this relationship pretty nicely, actually, if you ask me, in my opinion. So using the equation for a line then, we could write down the relationship as follows. So we would say, I'll say y, I'll put a y prime there. It's not meant to be a derivative or anything, but it is sometimes you'll see like y hat. Sometimes you'll see y prime is not uncommon. And I'll say w1x1 here. This is mimicking the slope-intercept form of a line y equals mx plus b. With just some slightly different conventions on the notation. So what we have here is, I would say, then this is our predicted value or label. What do we have here? A b term. This b term is your bias or the y-intercept, sometimes referred to as w0. So we'll call this bias or the y-intercept, sometimes called w sub 0, where the w is typically here. In this case, we just have the 1 w1. w1 is the weight of future x1. Oops. Is the weight of future x1. So, and you would have, if we talk about getting into more features there, but x1 then is the feature or input or what we're using to help predict the value. In that case, that's our square footage right here. So this is our future. Okay, so it's a good start. That is a good start. So a simple equation of a line, and we put the hat or the prime there to indicate that it is just an approximation. It's not necessarily a true value in our data set. More sophisticated models might rely on multiple features, and that still what ends up being a linear regression model. And we can talk about more what it means to be linear here, but let's just write this down for a second. More sophisticated models might rely on multiple features. More sophisticated models might rely on multiple features. And those would look like as follows. So we would just have our single bias term or intercept, plus you have W1x1, and then you're going to have W2x2, and a weight W3 for a third input, so on and so forth. Let's say we have K different features we would want to use to help predict the price of the house. And so this is something that might make sense if you could think about what would go into the price of a home, right? So you could have like not just square footage, right? But you might have like the lot size, right? So you might want to take that into consideration. You might have does it have a garage or not? Like, how updated are the appliances? Like, how nice is it? I don't know. How many different bedrooms, how many bathrooms does it have, right? Those are all things that you would go into modeling the price of a house. It's a little bit harder to visualize at that point, but that's essentially what we're looking at here, okay? Okay, good. So that is a good starting point for the linear regression basics there. So now let's talk about training and loss. Training and loss, and what we mean by training. So when we are going to go through and figure out how to fit this line, this best fit line here, we're going to take a iterative approach to doing that. And so we're going to use a machine learning style approach here, which actually we'll see where we can jump off and do it with ordinary least squares, which is more traditional statistical methods. But just some terminology that is probably more from the machine learning side of things rather than the true statistical side. Training a model means determining the values for all of the weights and bias terms that you would have in your model. So let's go ahead and define that. Training. Let me clean this up a little bit. Training a model means determining the values for all the weights and biases from labeled examples. Values for all the weights and bias from labeled examples. So in that case, we're looking at what is the value for B? What should the weight on X1 be? So what should W1 be, W2, W3, and WK, so on and so forth. And we're going to use labeled examples to help figure out what that should be, right? So I can look at a specific data point, like I can look at a specific house and say, okay, this house has 2,000 square feet, it's 3-bedroom, 2-bathroom, and it's on a half-acre lot. And then that house is priced at, blank $100,000. That is one sort of data point that I could use to figure out what things I might need for these values here, okay? Now, loss is a number indicating how bad the model is. Loss is a number indicating how bad the model prediction was on a single example. Loss is a number indicating how bad the model prediction was on a single example. On a single example or case in our data set. So if the model is perfect, an exact prediction, then the loss on that would be 0. So let's just say this here, right? Just to get an idea. If the model prediction is perfect, then the loss is equal to 0. So for example, if we go back up to our data set here, there's a couple of data points where it looks like the loss might actually be 0, or really close to 0. And that would be there's a point right there. I don't know if you can see my cursor. There's a point here towards the top of it. And towards the bottom, the second data point looks like it's the line's just above it or pretty much on top of it. That's pretty much 0 loss right there as well. But some other ones have some significant loss, right? So for example, there's a gap right here. And so that would be some loss, right? The distance from that point there, right? Here is, this one would be some loss too, right? That would add some significant. So if you looked at that example, that would show some significant loss, right? But if I move the line to fit this top data point exactly perfectly, right, then what's going to happen is it'll lower the loss for that case, but for these other examples, shifting the line up might increase the loss there, right? So you have also some loss in that direction as well, right? You can see we have some substantial loss right here. So that gap, that distance, is sort of some error, and that would be loss. So what we're going to do is try to minimize that loss, but we want to minimize that loss in kind of an aggregate way, right? And again, to kind of get back into a little bit of a machine learning approach, we'll talk about what the supervised machine learning algorithm is trying to do, and that it is exactly focused on this concept of loss. So let me go ahead and write this down here as well. In a supervised machine learning algorithm, I always struggle to spell algorithm correctly. Is that right? I think that's good. Yeah. In a supervised machine learning algorithm, a model is built by examining many examples. Model is built by examining many examples and attempting to find a model that minimizes the loss across all of them. Attempting to find a model that minimizes loss across all examples. This process is something that's called empirical risk minimization. Let's write that. So it's called empirical. That's another word I'm never sure how to spell. Empirical, E-M-P-I-R-I-C-A-L. I think that looks good. Risk minimization. Minimization. Empirical risk minimization. Okay, so there we go. Loss. Now, there's definitely a couple different ways we could talk about computing loss. I'm going to go ahead and introduce a common one, and that is the squared loss. Squared loss, L2 version of a loss function here. This is a popular way of computing loss, but it's not the only one. So one of the things you might notice here is if you look at the example that we had is on this higher data point right here, the distance from this point to our line, that's maybe some number. But the distance on the points that are below the line are going to have the opposite effect. So if this unit is 10 units above the line, this unit is minus 4 units above the line. So if you just add those things together, you're going to have some positive and negatives canceling out. And that's not really what we want to do. We want to sort of aggregate it. So we want to think about this in terms of like a distance, right? So I don't really care if it's to above the line or I don't care if my line is above or below the point. All I care about is how far away it is. And so there's a couple ways you can do that. One common way to do is just to square things, right? You could also do absolute values or some other more complicated techniques, but L2 is very common, and it's what we are going to use in this case. So it's a popular way of computing loss, but it's not the only one. So popular, but not the only. It's popular, but it's not the only way. So we're just going to square the difference of that distance, right? So we're going to go ahead and say our loss, which I might just start abbreviating as capital L here, is going to be the actual observation value, our actual home price observation value, minus the value that our model is predicting. Observation minus prediction. And again, to deal with the fact that we want to aggregate these things in a way so that we're not canceling out pluses and minuses, we're going to square that so all these losses are considered positive. Or are going to end up being positive, right? So in the notation that we had above, this would be our observation is just our Y value, our house price, and then we use this notation for the prediction value right there, and we want to go ahead and square that, and then we're good to go. So if that's our squared loss, then how do we go ahead and aggregate these things together? I'll change colors here. Let's try light blue. We will aggregate and add things together and take a look at something that is called the mean square error, or the MSE. Now, there are other ways to aggregate stuff, so you're adding things together. You could just simply sum over stuff. Mean squared error is just one step beyond summing things over. Sometimes you can also see halved mean squared error as well as pretty common. But essentially what we're doing here, when you see the word mean, we want to associate that with an average, right? So this is our average squared loss per example. Average squared loss per example over the whole data set. So we calculate MSE, average squared loss, for example, over the whole data set. So we can start by just simply adding everything up. So I'm going to leave some spaces to write this out. So we're going to use our summation notation, which means we're going to add everything together. So we're going to take our Y value minus the predicted value for X. So I will say, I'll just write out the predicted value for X. So Y minus the predicted value squared, that is just our loss, our squared loss. And the summation means we're going to do that for all of the data points, right? So we're going to add these all together. So we're going to sum over all of the ordered pairs X and Y in our data set D. And then the averaging part is if we had n cases to look at, then we would divide by n or multiply by 1 over n. Okay. There's other terms that arise from parts of this calculation, like just the summing would give you the sum squared error. You'll see these abbreviations in traditional statistics like SSE, SSR, and stuff like that. And a lot of them are just different components of this these calculations here. But to get specific to what we have on the screen right now, capital D is referring to our data set. capital N is referring to the number of cases in our data set D, in our row D, number of cases. X and Y, and XY is going to be a single case in our data set here. A single case in our data set. So X is the set of features the model uses to make the predictions. So again, we will start with simple regression where we only have one feature like square footage and try to predict the house, but we will get to things where you want to add in more features. And so before I'm using vector notation, I'll just say X is the set of features the model uses to make predictions. X is the set of features the model uses to make predictions. So what I'm basically saying here is I don't want you to just think of X and Y here as an ordered pair, like in two-dimensional space per se, even though I'm kind of writing it loosely in port notation. But Y is the observed value. Y is the observed value or label on that point. And obviously the PRED, the prediction of X, then is what the model would predict. This is a function of the weights. It's a function of the weights and bias in combination. Function of the weights and bias in combination with the set of features in X. With the set of features in X. Okay. When it comes to actually calculating this at the end of the day, Y is an observed value. That's a number. The predicted value for X, if we're talking about like a linear regression for house price, is just going to be a number as well. But when it comes to sort of generalizing and coming up with more formulas, it's good to think about that, what this is, because in some sense you want to be able to manipulate things and knowing what's going into that. So this predicted value of X, in this case, is going to be like a linear function like what we have up here in white. Okay, so what are we at here right now? We're at about a little over 20 minutes here. The last thing I want to do then at this stage is introduce the idea of once one calculates this loss, how does one go about trying to reduce loss and improve it, right? You can imagine you could come up with any number of linear equations here to fit these data points, right? Square footage and price. So I could have a variety of different lines that could go through this, and I could calculate the loss for each of them. So I could say, what if I try a line that goes like up here? I could try a line maybe that goes, like that as well. And I can calculate the loss for all of these. And, you could compare them. And this calculating that mean square error does give you a way to compare how good of a fit a line is and actually sort of say, well, the green line is better than the blue line, for example, right? But we don't really want to do completely just guessing and checking, because how do we ever know that we found the best line, right? So we're going to take a little bit more of a little bit more sophisticated, although surprisingly not that sophisticated overall, but we'll have a process, maybe is a better way to say it, of figuring out what is a good fit for that line. So let's start a new section here. I'll go back to yellow for this. My new section on reducing loss. Reducing loss, okay? And the idea here is to take an iterative approach. An iterative approach. So here's the general idea for how we want to reduce loss. Okay, let's just start out with the idea. Iterative learning is a bit like the hot and cold guessing game. I'll write this down. Iterative iterative learning, when it comes to supervised learning, is like a hot and cold guessing game. Is like a hot and cold guessing game. Right? So we're going to start out with, we do have to start out with an initial guess. Okay, so we will start out with an initial guess, say W1 equals 0. Okay, so for context, right, what are we thinking about here? We're thinking about, let's just take the simple case. We want to know what we should be using for B and W1. I'll just consider one parameter W1 here at a time for now, but so I'll just set that equal to 0, right? And basically the idea is you take a guess and see what it is, right? So maybe that is a cold guess. So when you do the hot cold guessing game, right, you start with a guess and you kind of get a hot or cold. So we'd modify our guess then, right, from that. So then we'd modify and try something else. So I don't know what else we want to use. How about 5? W1 equals 5 here, right? And then so maybe we get a result here, and that is maybe not correct, but it is warmer. Okay, so we're going in the right direction. So that's warmer, right? If it was colder, for example, you would know you're going in the wrong direction and you'd want to reverse the behavior. So 5 is warmer. Good, we're going in the right direction. So if I were to try, and then I'll try a guess for W equaling 10, and maybe that, is less warm. Less warm or cool probably would be the right, we went from warm to, cold, from warm to cool. So, okay. So what that means then is we've gone too far, right? So this is, too far. So we go back. And maybe we try somewhere between 5 and 10, like let's try 7. We try 7, right? And then all of a sudden that is, and that's a hot. Okay, so we're getting really close. We're getting really close then, right? So this is the iterative approach to reducing loss. We'll start with an initial guess for the weights and bias, and then we're going to iteratively adjust those guesses until learning the weights and bias with the lowest possible loss. So I'll just write that down again here. So we start with an initial guess. Start with an initial guess for weights and the bias term, right? And iteratively, that looks good. Adjust those guesses. Just those guesses until learning the weights and bias with the lowest loss. Until learning the weights and bias with the lowest loss. Okay, so that is the general idea so far in terms of what we have. So again, to continue along with this in a deep dive approach, right? Take the simple model, our model of y equaling our bias just with one input feature, okay? There is some details that are really kind of interesting here, depending on your background, that you might be thinking about in terms of this hot and cold guessing game is, how do you know you don't get to a false sort of minimum? I guess is one way to kind of, I don't know, I'm trying to think about in terms of, you could plot your loss function, right? And maybe if this is my loss, right, you want to get to here. How do you know? You go, you're going warmer, warmer, warmer. You get to here, and then you go back here, like, oh, I'm getting colder. And you start going back here, but really you want to go down to here. That's really an interesting thing to think about. But for linear regression models, it turns out that where you start is actually not necessarily as important in terms of we don't really have to worry about starting in a bad spot and falling into that false valley or local minimum when you're looking for a global minimum. So I'll go ahead and just write that out as well. For linear regression, it turns out that the choice of starting values, for your bias term and your W's aren't that important. It can you can choose good values that can help speed things up. But in terms of is it going to be a fatal error? I think the answer is no there, right? So something that we're going to do as we continue this deep dive into understanding gradient descent later is to get some concrete values is we'll probably just start with values of 0. Start with b equals 0 and w1 equals 0 as well. Right? So for any input value x1 that we might have in an observation, so for any square footage, right? So for any feature value x1, we're going to have the prediction is going to be 0 plus 0 times x1, which is going to be 0. So in that case, our squared loss is y minus the predicted value, which in this case, if we start with 0, it's always going to predict that. So our squared loss is just the actual value that we observed squared, which sort of makes sense, right? Where y equals actual value for that case. Okay, so then we have a loss. We have an actual number for that loss. We update our guess for B and W1 and compute the loss again, right? So then update values for B and W1 and compute loss again. And that's the kind of the big idea for this iterative approach. Typically, you iterate over and over and over until the loss either stops changing or is maybe changing at least extremely slowly, that you're sort of close enough, right? You're only moving the loss by 0.000000001. When you're doing these iterations, you might say I'm close enough. I met some threshold, right? So typically, you iterate until overall loss stops changing. Overall loss stops changing, or is at least changing extremely slowly. Or is at least changing extremely slowly. This is the idea of converging or convergence. That was our iterative approach is converging. We are converging on a solution for our parameters there, okay? And I think I want to leave it at there for this opening deep dive to go along with the three-part video series on implementing linear regression via gradient descent. So not much extra really this first one, but in the next one where we're going to go ahead and we'll actually get into knowing this idea, this method of gradient descent in terms of when you update your values here. I'll leave you with this. If you haven't watched that and you don't know where you're going, when we update our values, we don't actually need to just do a guess and compute the loss and compare it to the previous one. We could actually use something called gradient descent to know when we update these values that we will be reducing the loss and we will be moving in the right direction. So I don't need to do that comparison between the previous loss and the current loss to know if I made an improvement. I can just say, take what I'm at and know I can go into the correct direction. Which is really might seem kind of magical at first, but that's pretty cool. So we'll leave it for that next deep dive, and we'll get into that. Okay, hope to see you then.